Hi, greetings everyone. My name is Elsa Vieira and I'm a researcher in food chemistry and sustainable foods at the School of Engineering of Polytechnic of Porto in Portugal. The topic of this lecture is design of eco-friendly bioplastics and biocomposites from chestnut waste to green materials. The lecture is divided in two parts. Today I will focus on development of bioplastics. This lecture is part of the AGRIMA project, Agri-food Waste Management for Sustainable Bioeconomy through Higher Education, Curricula and Upskilling, which aims to foster universities' capacity building for the green transition by updating higher education curricula and developing innovative practice in agri-food waste management for a circular bioeconomy. It addresses different aims. Here you can see all the international academic institutions that are members of the AGRIMA project. The School of Engineering of Polytechnic of Porto is one of these partners and it is where I work. The School of Engineering of Polytechnic of Porto is about 6,000 students, making it one of the largest and most important engineering schools in Portugal. It offers undergraduate and postgraduate programs across a range of departments. You can find more information about our institution by following this link. The school covers a broad spectrum of scientific and technical fields and is home to numerous research centers and laboratories. GRAC is a research center that belongs to the Chemical Engineering Department and comprises an interdisciplinary team focusing on three main areas: analytical chemistry, quality control, food safety, environmental monitoring, biosensors, environmental remediation, cleanup of contaminated soil and water, and sustainability, life cycle analysis, waste resource management, and risk assessment. GRAC is integrated in the National Requinte Network, the Portuguese Research Center for Sustainable Chemistry. Requinte is focused on three main research lines: the development of cleaner, safer and more environmental friendly chemical process and products, the enhancement of food quality, ensuring authenticity and effectively controlling of allergens, additives and chemical contaminants, and advances in human health through novel solutions in disease diagnosis. My research has predominantly been driven by environmental chemistry. Turning back to the topic of this lecture, let's start with a brief introduction about the problem of the synthetic plastics and the urgent need to find more sustainable alternatives. Plastics are ubiquitous materials in our daily lives, from packaging and clothing to automotive components and medicinal devices. We are also using plastics. However, their life cycle from production to disposal has a significant and lasting impact on human health and environment. In fact, only about 9% of plastics are recycled. The rest is disposed in landfills and discarded in the environment or also incinerated. And this disposal can release harmful components in soil, water, and air. A key problem associated with bioplastics is their breakdown into tiny particles called microplastics. to the physical, chemical, and UV effects. Microplastics permeate all components of the environment, from freshwater lakes and agricultural fields to the deep ocean, and enters in the human body, acting as carriers for hazardous chemicals and microbial pathogens. So they can cause inflammation, cellular damage, and oxidative stress, and may contribute to health disorders. So, designing sustainable plastics is a sustainable approach to reduce the consumption of synthetic plastics. Bioplastics are materials made from renewable sources, partially or entirely, and predominantly from natural polymers. So, a lot of research has been exploring this path using promising polymers from animal, vegetable, and microbial sources in bioplastic design. The goal is to find full and biodegradable materials capable to reduce the dependency of fossil fuels. So we want to make research to this goal. The chestnut industry produces large amounts of agricultural waste, as non-commercial chestnuts, shells, leaves, and burrs, which can serve as a valuable resource for this application. In fact, Portugal here it lists the 5 main European producers of chestnuts, being the production most concentrated in Trás-os-Montes region, which accounts for over than 80% of national production. According to RefCast, here is the source, about 44,000 tons of chestnuts are produced annually, valued at about 65 million euros, a figure that is expected to reach 150 million euros by 2030. From this production, 6 to 7% of this production has no commercial value, such as small, defected, or rotten chestnuts, while 19% is sold fresh and 74% is processed, generating byproducts such as shells and small fragments. All these products collectively represent 40 to 50% of economic losses, valued at around 24 million euros, underscoring the potential for its valorization. Besides the fruit and chestnut shells, also the burrs, flowers and leaves are also rich sources of biocompounds with potential application in bioplastics. For bioplastics applications, the non-commercial fruits can provide the starch to form the polymer matrix, while the shells and burrs, which are rich in cellulose, can act as reinforcement, as fillers of bioplastics. Also, these byproducts, especially burrs and shells, contain bioactive compounds that can functionalize the films, having antioxidant and antimicrobial properties. Chess Film is an ongoing project at the School of Engineering of Polytechnic of Porto that aims to develop biodegradable films from polymers extracted from chestnut byproducts. The project is supported by La Caixa Foundation and the Portuguese Foundation for Science and Technology through the fourth edition of the Promove program. It is a consortium of Requinte, represented by the School of Engineering of Polytechnic of Porto, University of Aveiro, also a Portuguese institution, and Sortgel, the leading Portuguese industry for chestnut production and processing. Let me introduce the chest film research team from ISEP, from Institute of Polytechnic of Porto. Cristina Matos, the leader of our research group. Valentina Domingos, principal investigator of chest film. Myself, Olga Freitas and Helena Surra, researchers, and Samara Rodrigues and Simão Batista, hired investigators. In this lecture, I will focus on recent advances in the extraction of fibers and polyphenols from chestnut shells for incorporation into films, which were subsequently characterized and applied as a packaging for a food model. So, regarding the experimental part, this figure illustrates the sequential extraction of cellulosic fibers from chestnut shells, which involves dehydration, mill, sieving, bleaching, washing, and drying steps. To make this process more environmentally friendly, we optimize a green procedure that avoids the use of alkaline treatments at high temperatures and toxic bleaching agents. The final dried cellulose fibers are shown here, and some images reveal that chestnut fibers have an average diameter of 20 to 17 micrometers and form strong interactions with the polymeric matrix. In fact, preliminary results were presented in this publication which evaluated the effects of adding lignin and chestnut-derived fibers as reinforcement to starch-based films, and these are the comparison of films, the control films with no fillers, and the optimized film having cellulose fibers. In fact, data show that the reinforced films demonstrated tensile strength and Young's models nearly 3 times greater than the control film, and also exhibited improved UV barrier properties, water resistance, and thermal stability. Chestnut shells bioactive compounds were extracted by subcritical water extraction following established procedures. The full publication is available at this link. The process was carried out at 220 Celsius degrees for 30 minutes under around 15 bars of pressure, with a solid to water ratio of 1 to grams per 10 milliliters of water. The chestnut shell extract is rich in tannins, caffeolinic acid isomers, and other phenol compounds, and also shows strong antioxidant activity in various in vitro assays. Here we can see the equipment used. alongside the lyophilized extract and the extract solutions that we incorporated into film. The films were prepared by solvent casting technique using commercial potato starch as the base material, 50% of glycerol relative to starch as the plasticizer, and 20% of cellulose fiber relative to starch as the reinforcing filler. A combination that effectively improved the mechanical properties of the film, as I mentioned before. Briefly, after the starch is gelatinized by heating at 90 Celsius degrees for 30 minutes, the film forming solution is degassed to remove air bubbles, and once cooled, the extract is heated at different concentrations. We tested 2, 4, 8, 16, and 20 milligrams of extract for each 100 milliliters of filmogenic solution. The mixture is then poured into a mold with the amount carefully calibrated to produce thin films and placed in a convection oven under controlled temperature and air circulation conditions for water evaporation. The film is subsequently removed from the mold and conditioned. Some illustrative videos and images show this procedure. Here, the fiber is weighed and dispersed in distilled water. Then it is treated with ultrasound to weigh the dispersion of fibers in water. And then in another container, the starch is weighed and dispersed in water and also heated at 90 Celsius degrees for 30 minutes to allow gelatinization. After cooling, both solutions are blended and incorporated with the extract solution. And here we are having the extract solution in this video, and the final film forming mixture is then poured in a mold, and as I told you, the amount is carefully calibrated to produce thin films, and then placed in an oven under air circulatory conditions. And once the water has evaporated and the time and temperature conditions for this step is also optimized, the film is removed and conditioned. So these are the functional films developed with different concentrations of chestnut shell extract. As we can see, the control film is transparent and homogeneous, and the addition of extract 2, 4, 8, 16, and 20 milligrams for each 100 milliliters of film forming solution results in films with a brownish color, but that remain equally transparent and homogeneous and free of defects such as air bubbles or scratch. The films were characterized in terms of mechanical properties, also optical properties, barrier properties, and antioxidant properties. But we are now measuring other properties also important to characterize the films. For a brief review, the mechanical properties of films are key indicators of their ability to perform under stress and handle mechanical loading in packaging applications. In fact, thickness is particularly important, an important parameter, because dimensions directly affect stress and stiffness calculations. Thickness is typically measured at multiple points of each film sample using a micrometer, and the average thickness is then used for further calculations. The mechanical properties, such as the tensile strength, the Young's models, and the elongation at break, are measured using a tensile tester. And this is the photo of the tensile tester that we use in our measures. Briefly, the tensile strength of the film reflects the maximum stress that a film can sustain under tension, and is expressed as a force for a night area. Young's models reflect stiffness, so a great Younger models means greater resistance to deformation under an applied force, and the elongation at break expresses a film ability to scratch without tearing, indicating that it remains flexibility alongside improved strength. The optical properties of the films are typically measured with a UV spectrophotometer. Samples are placed directly in the sample holder, and absorbance is scanned across the UV and visible range. The UV barrier properties reflect how much UV light, typically in the 200 and 400 nanometers range, a film can absorb or block. So higher absorbance in this range corresponds to greater UV blocking, which is desirable for protecting light-sensitive food components from photooxidation. Opacity quantifies a film's ability to diminish visibility or allow light to pass through the film. It is often defined by measuring the absorbance at 600 nanometers and divided by the thickness of the film to normalize the values. So higher values indicate an opaquer film, which may be desirable in packaging applications where light protection is required. A packaging material is considered recoverable through composting and biodegradation when it complies with standard legislation, and to be classified as biodegradable, a film or a bioplastic must break down, this is definition, into carbon dioxide, water, and biomass under composting conditions. So at least 90% of the material must be biodegraded in aerobic conditions within 6 months when compared to a control material. To be considered disintegrated in the soil, the packaging must physically break down into tiny fragments, and after 3 months at least of industrial composting, 90% of the material must pass through a 2 millimeters sieve. and to be classified as environmentally friendly. The resulting compost must show no toxic effects on agar plants, so germination and growth tests, such as grass or barley, should show at least 90% germination and biomass when growth in soil amended with compost. Furthermore, heavy metal content must be below specific limits, and also the total fluorine content should be below, and the volatile salts must be above 15%. And these are the current chemical analysis standards for bioplastics. In this work, films were put in contact with a standard soil for 5 weeks and waited once a week to evaluate the degree of disintegration in terms of weight loss. And synthetic plastic, the polyethylene terephthalate, was used as a control test. The reinforced film functionalized with 90 milligrams, with 20 milligrams of chestnut shells extract was applied to a food models, and cookies with 7% of moisture content were packaged with control and functionalized films for 4 weeks under 3 controlled conditions to mimic the commercial storage conditions of this kind of products. So 25 Celsius degrees with light exposure, 25 Celsius degrees in the dark to mimic cookies packaged in plastic that are covered via paper box, for example, and 30 Celsius degrees with light exposure to mimic weather seasonal variations. Also, for comparative purposes, cookies were packaged with synthetic film, and after contact cookies with cookies for 4 weeks, films were evaluated regarding some performance in terms of mechanical properties, moisture and water solubility, and we also done migration studies through in vitro antioxidant assays. Now I will present some of the results related to this evaluation. The addition of chestnut shell extract resulted in a reduction of tensile strength and elongation at break of the reinforced films and functionalized films. However, this effect was less pronounced at the highest concentration tested, which were 20 milligrams of extract, suggesting that incorporating higher levels of chestnut extract, despite affecting the color and appearance, may be a viable way to maintain the mechanical performance of the film. So this is certainly a direction worth to explore. Also, the addition of chestnut extract didn't affect the water solubility. However, when it added at concentrations above 4 milligrams, as we can see here, it made films opaque, offering greater protection against light and UV radiation. This may occur because the extract contains polyphenolic compounds and tannins, which naturally absorb UV light and reduce transparency. So this phenomenon can be desirable in packaging applications to prolong the shelf life of light-sensitive products in bioplastics application. Regarding the antioxidant properties of the extract, we see that the total phenolic contents and the antioxidant activity of the films were significantly enhanced by adding the extract, as we can see here, at 20 milligrams of extract incorporation. Films contained more than 6 times of total phenolic compounds and demonstrated a much higher antioxidant activity than the control film. Biodegradability studies were also performed, and as I mentioned, films were placed in soil for 5 weeks and water once a week to evaluate their degree of disintegration by weight loss. Here we can see the films after contacting soil for this period. And results show that the functionalized films were less biodegradable than the control film, but they were biodegradable overall according to the international standards. Important to reinforce that to accomplish the standards, this contact should be at least for 6 months, and this was only tested for a period of 5 weeks. Regarding the application of the functionalized film to package cookies with 7% of moisture at different conditions for 30 days, let me show the major findings. This is the appearance of plastics and cookies at day 0 and after 30 days of contact. And for an example, this is the graph that shows the water content comparisons of bioplastic with cookie, bioplastic, and only cookie after 30 days of study. So the green bars, or let's start with the blue ones. The blue bars represent the bioplastic in contact with cookies for 30 days. The green bars shows the control bioplastic that were without contact with cookies, and the gray bars reflect the cookies water contact directly. So overall results showed that there is no significant change in the water content of cookies across different temperature and light conditions. Furthermore, the packaging film, whether in contact with cookies or not, the blue and the green bars maintained its water content fairly consistently. So, in conclusion, the film's application didn't affect the cookie's water content and remained stable under storage conditions. The same observation was obtained for other evaluated parameters. Overall, for all the conditions tested, the functionalized films maintained water solubility, Young's metals, and UV barrier capacity. So, results suggest that the film maintained its functionality and protective properties during 30 days of storage with this type of food. So, in summary, The chestnut shell subcritical water extract was successfully incorporated with a reinforced starch-based film. The functionalized films showed good mechanical performance and improved UV barrier and antioxidant properties compared to the control film. After 5 weeks in soil, the functionalized films demonstrated 13 to 16% of disintegration. The functionalized film, when used to package cookies with 7% of moisture content for 30 days at 25 Celsius degrees and 30 Celsius degrees under both light and darkened conditions, maintained its mechanical performance and also its UV barrier and protective effects. And the cookies remained visually appealing, keeping their color, moisture contents, and sensory attributes for this period of contact with bioplastics. So, overall, the recent advances in chest film development show that it is viable to convert chestnut shells into eco-friendly and functional packaging solutions. We are now exploring new ways to improve the hydrophobic properties of these bioplastics, allowing their application to a wider range of food products with different water content. In fact, we have already begun testing new fillers and hydrophobic additives to achieve this. So, this is my lecture. Thank you all for your attention, and please feel free to contact us to know about more information about chest film project and any doubt if you have. So, and please, we appreciate if you could take a minute to evaluate this lecture using this available QR code. Regards, and please assist the part 2 of this topic, and thank you again for your attention.